Hi everyone. Today we'll learn how to compute limits algebraically. Let's start with a quick exercise. What are the limits of the following two functions? If you would like to try this exercise on your own first, you can download these notes using the link in the video description. To compute the first limit, I use the direct substitution property, which means I plug in 2 to the numerator and to the denominator. That gives me in the numerator 11, in the denominator -1, so the limit is -11. In the second example, I also apply the direct substitution property, and I get 2 squared minus 4 divided by 2 minus 2. This gives me 0 divided by 0. This means that I was not allowed to use the direct substitution property. You can only use the direct substitution property with rational functions if the denominator does not give you 0. If the denominator gives you 0, the direct substitution property doesn't apply. So instead of using algebra here, I will use a table and a graph. Below, you can see the few values of this function around x equal to 2. Note that as x's get closer and closer to 2 from the left, the y values get closer to 4. As the inputs get closer to 2 from the right, the y values, the outputs, get closer to 4 as well, which suggests that the limit of this function is 4. Note that the graph says the same thing. As x's get closer and closer to 2 from the left, the values of the function get closer to 4. As x's get closer and closer to 2 from the right, the values of the function get closer and closer to 4. Note that it makes sense that there is an open dot here. The function x squared minus 4 divided by x minus 2 is not defined at 2. Even though it's not defined at 2, it appears that the limit of this function at 2 is 4. Can we confirm that algebraically? Let me rewrite this limit on the right side, so I get the limit as x goes to 2 of x squared minus 4 divided by x minus 2. I am going to use a famous formula to factor the numerator. I believe that a famous formula that people know is a squared minus b squared. You can rewrite that as a minus b, a plus b. I want to use this formula because I see that in the numerator I have x squared minus 4, which is the same thing as a squared minus b squared, where b equals to 2. That means I can rewrite the numerator as x minus 2, x plus 2, divided by x minus 2. Now I see that I have a factor of x minus 2 in the numerator and in the denominator. I can divide it out, and I get the limit of x, as x goes to 2, of just x plus 2. Now nothing is stopping me from applying the direct substitution property. I plug in 2 and I get 4. What's the conclusion? The conclusion is that when you get an indeterminate form of 0 divided by 0, then to compute the limit, you often have to apply some algebraic manipulations before applying the direct substitution property to compute the limit. I will show you a few examples of algebraic manipulations that lead to a correct answer. Let me first tell you why you are allowed to cancel the factors in the numerator and in the denominator. After all, the function x squared minus 4 divided by x minus 2 is not the same as x plus 2. Take a look below. The function x squared minus 4 divided by x minus 2 is different than the function x plus 2. The two functions look differently. In fact, they are the same almost everywhere, but at x equal to 2. The function on the left is not defined at x equal to 2. The function on the right is defined at x equal to 2, which means the two functions are almost identical besides at one point at x equal to 2. In that case, we say that the two functions are not the same. However, their limits are the same at x equal to 2. Note that as x's the inputs approach 2, the outputs approach 4 in both cases. This is the entire idea behind algebraic manipulations. Even though the functions are not the same, their limits at the point of interest, at the point of x equal to 2, are the same. So if you ever get a function whose limit is difficult to compute because it gives you an indeterminate form of 0 divided by 0, instead you do some algebraic manipulations, you create a new function which is almost the same as the original one. It differs from it only in one place, but the limit of that new function is the same as the limit of the original function. Now let's see if we can apply the algebraic manipulations to compute limits of 3 functions. In the first example, I have the limit of this rational function as x goes to 5. If you would like to try this exercise on your own first, this is a good time to stop the video. I see I cannot plug in 5. If I do so, in the numerator I will get 0, and in the denominator I will also get 0, which gives me an indeterminate form, a form that is still yet to be determined. So to determine that limit, I take the limit as x goes to 5, and I realize that in the denominator I can factor the denominator. I can rewrite this as x minus 5, x minus 1. If you multiply out these two parentheses, you will get x squared minus 6x plus 5. And if you don't remember how to factor polynomials, I hope to record one day a video about factoring polynomials. Now I see that in the numerator and in the denominator I have x minus 5. So I divide out those two terms and I get limit as x goes to 5 of 1 divided by x minus 1. And the 1 in the numerator is there because x minus 5 is the same thing as x minus 5 multiplied by 1. So when x minus 5 gets divided out, 1 stays there. Now nothing is stopping me from applying the direct substitution property. I plug in 5 and I get 1 divided by 5 minus 1, which gives me 1/4. Let's try one more example. Here I have the limit as x goes to 5. Now, if I plug in 5 to the numerator, I get 0. Plug in 5 to the denominator, I also get 0. This is an indeterminate form of 0 divided by 0, which means I have to apply some algebraic technique to compute this limit. The algebraic technique we use with square roots is called multiplication by a conjugate. What I'm going to do is I will multiply this expression by 1. But I will not write it as 1. There are various ways of writing 1. Instead of writing 1, you can write 5 divided by 5. You can also write x plus 7 divided by x plus 7. That's also another way to multiply this expression by 1. What I am going to multiply it by is what I have in the numerator, but with a plus sign between the two terms instead of a minus sign. So I will multiply it by square root of x minus 1 plus 2 divided by the same term, square root of x minus 1 plus 2. The reason why I'm doing it will be clear in a moment. Just an explanation why it's called a conjugate. If you have an expression 2 plus x, the conjugate of that expression is 2 minus x. If I give you an expression 3 minus 5, the conjugate of this expression is 3 plus 5. So a conjugate of an expression is two terms with a different sign in between them. So that's exactly what I did here. I had an expression in the numerator with a minus sign between the two terms. I replaced that minus sign with a plus sign. So I'm multiplying the top expression by its conjugate in the numerator, and then I'm also adding the same conjugate in the denominator. This is a fancy way of writing 1. I do that because now when I multiply out the numerators, things will simplify. In the top, I'm going to use this famous formula, a minus b, a plus b equals a squared minus b squared. We already mentioned that formula. Note that you have a and then you have b. So you have a minus b times a plus b. Here's like a, here's b, here's a, here's b. When I multiply them, I get a squared minus b squared. So I get a squared minus b squared. So that gives me the limit as x goes to 5 of, if I square the first term, square and square root cancel each other, and I just get x minus 1. When I square the second term, I get 4, so I get minus 4. Everything gets divided by the two denominators multiplied by each other. So I get x minus 5 multiplied by square root of x minus 1 plus 2. In the numerator, I get x minus 1 minus 4. That gives me x minus 5. So x minus 5, I can cancel with this x minus 5. That gives me the limit as x goes to 5 of 1 divided by square root of x minus 1 plus 2. Now, nothing is stopping me from plugging in 5 to this expression. I will no longer get division by 0. And I get 1 divided by square root of 5 minus 1 plus 2. 5 minus 1 is 4, square root of 4 is 2, so that gives me 1 over 4. I want to point out how I kept rewriting the word's limit up until I used the direct substitution property. The word's limit disappeared only after I plugged in 5 to my expression. I have one more example for us. Now we must find the limit as x approaches negative 3. Note, when you plug in negative 3 to the denominator, you get 0. You plug it into the numerator, you also get 0. Which means this is an indeterminate form. We must first apply algebraic manipulations. At the top I have a fraction, and I have to add 1 to it. I will find a common denominator. So instead of writing 1, I will write x plus 2 divided by x plus 2. So that will give me the limit as x goes to negative 3 of 1 over x plus 2 plus x plus 2 divided by x plus 2. All of that divided by x plus 3. Now the two fractions in the numerator have the same denominator. So I can add their numerators. 1 plus x plus 2 gives me x plus 3. So I have x plus 3 divided by x plus 2. All of that is divided by x plus 3. Now, dividing by x plus 3 is the same thing as multiplying by its reciprocal. For example, 4 divided by 5 is the same thing as 4 multiplied by 1/5. 6 divided by 8 is the same thing as 6 multiplied by the reciprocal of 8, which is 1/8. The same thing here. Dividing by x over plus 3 is the same thing as multiplying by 1 over x plus 3. So this gives me the limit as x goes to negative 3 of x plus 3 divided by x plus 2 multiplied by 1 over x plus 3. Now, x plus 3 in the numerator and in the denominator, they divide out, which gives me the limit as x goes to negative 3 of 1 over x plus 2. Finally, I plug in negative 3 to my expression using the substitution property and get 1 over minus 3 plus 2. That's negative 1, so I get negative 1.